The Murphy Group of companies combines experience, effective management and expertise to provide the highest standards of service to clients across a wide range of construction and engineering activities. Launched in 1969, Murphy Pipelines is one of the subsidiary companies that make up the Murphy Group, founded by John Murphy in 1941. Barrow to Lupton, Mossmoran to Brayford Bay, Peterborough to Huntingdon, Cleve to Didcot. Just 4 of the major gas, oil and water pipeline projects recently completed to demanding schedules by Murphy Pipelines. Major cross-country of mine and mains and services, urban pipelines of all sizes, petrochemical plants, gas compressor stations and water storage and treatment facilities. Up-to-date techniques and the latest plant and equipment are utilized in all activities, from the replacement of cast iron mains to the use of self-driven, all-terrain chain-driven excavator loaders for minor mains. Later, we shall be looking at Murphy Pipeline's methods employed in constructing the 57-kilometre Cambridge to Epping 900mm gas pipeline, which reflects the Murphy approach throughout the group of commitment to the environment and technical innovation, without sacrificing safety and quality. In the public and private sectors alike, Murphy have forged an enviable reputation for not only completing projects on time, but to exacting standards and safety requirements. Hence, a wide spectrum of activities are unified by a common underlying philosophy: total commitment to demanding customer requirements whilst maintaining minimum environmental impact. In civil and mechanical engineering, in tunnelling, pipelines, telecommunications engineering, together with building across the industrial, commercial and residential sectors. Such a philosophy means that the Murphy Group are constantly at the forefront of technology in several strategic areas. Murphy Tunnelling, for example, has played a vital role in completing the through rail link from London's Liverpool Street Station to Stansted Airport. A mechanised tunnelling shield and segment erector was used to drive the 6.2-metre diameter tunnel under the main airport runway. The route of the new railway spur was initially selected as the most cost-effective and environmentally acceptable option. Few motorists were aware, as they crossed a bridge section just to the north of Bishop Stortford, that below, a 1.8-kilometre rail tunnel was being cut at the rate of some 12 metres each day. This resulted in the project heavily in the most up-to-date technology to meet rapidly expanding activity in the wake of initial deregulation in the telecommunications and cable industries. The diverse repertoire of projects for major clients such as British Telecom, Mercury, cable TV companies and the various electricity boards encompass the installation of telephone boxes to the laying of complete cross-country networks. These major ongoing projects are carried out with the minimum disruption to the general public, which bears testimony to the considerable all-round expertise Murphy have developed in the fields of duct laying, cable laying and jointing chamber construction. Furthermore, excavation periods are kept to a minimum, as was the case with the Sellindge-Folkestone high-voltage crossland link, which now provides power backup during periods of peak demand. Commitment to quality is the hallmark of the Murphy service across all their divisions. Underlying this, an internal quality assurance system has been formalised to meet the rigorous demands of the British Standard 5750, in addition to any external statutory monitoring. This is well illustrated by the Building Division, who were recently awarded the National Housing Design Award for its building excellence. But by combining traditional construction techniques and finishes with the ever-increasing demand for the intelligent building, Murphy's expertise extends across the entire range of building projects. Recently completed projects range from a magistrates' courthouse, housing developments for various London boroughs, to one of the Docklands flagship projects, and aspects of the Bishopgate complex in the City of London. Other projects have also included the renovation of one of London's most famous sites, the statue of Eros in Piccadilly. Whilst care for the environment is an overriding consideration throughout the group, Murphy's also make a direct contribution to environmental protection through its own solid waste systems division. Murphy are not only consultants to worldwide projects, but have acted as the main mechanical and electrical contractor to 14 major British waste disposal projects, including Glasgow's Polmady Refuse Baling Station, Europe's first high-density municipal baling plant. Be it piling or property management, rock blasting, demolition, or manufacture of ready-mix concrete, extensive computerization and experienced project management means that the Murphy Group always deliver on time in a cost-effective manner. An efficient yet caring approach. Hence, it will come as little surprise that Murphy's is one of the top British construction companies with an annual turnover in excess of £130 million. Consistent growth through the last 50 years means that the group now employs more than 2,000 people with some net assets of over £30 million. Let's now take a closer look at the work of the pipeline division and see how the combination of technical innovation, careful project and quality management, and environmental consciousness has made this sector one of the largest net contributors to the group's reputation and performance. The Cambridge to Epping pipeline was another in a series of national feeder pipelines for British Gas, designed to transfer supplies to the points of greatest demand at peak time throughout the country. As a further part of the Southern Gas Supply Reinforcing Scheme, the contract involved laying approximately 57 kilometres of 900mm diameter welded steel pipes, together with civil, mechanical and electrical works to 2 new pig trap installations at either end. These are necessary for testing and maintaining the pipeline, but more about this later. 2 new block valve installations were also built. Through the use of specialised equipment developed by Murphy Pipelines themselves and the continuously moving assembly line spread approach, the mechanical completion of the project was actually completed 7 weeks ahead of the contracted schedule. The contract was awarded on April 2nd, 1990 and due for completion by September 15th, 1990, a period of 24 weeks. In fact, the pipeline was laid, land restored and handed back to the landowner by July 27th, 1990, a construction period of only 17 weeks. The 25 separate operations of the spread encountered the crossing of 31 main roads, 2 major railway routes and crossed the M11 motorway twice. But despite these many apparent obstacles, progress still averaged in excess of 1 kilometre a day for the individual operations. Let's catch up with the early stages, where we can already see intense activity in preparing the site. It took only 2 weeks from the contract award to mobilise the necessary resources and establish a temporary headquarters at Stansted Mount Fitchet. In effect, this means a skilled and manual workforce of 375 and some 280 items of plant, transport and equipment. And already setting out has begun. A working width or easement is established based on a centreline marked out by experienced land surveyors. A width of 36.5 metres is set out, which increases to 52 metres at special road, rail or river crossings. Setting out a right-of-way is not simply forcing a bulldozer through a strip of countryside. Murphy Pipelines pay meticulous detail to every aspect of the environment, ensuring that anything is not needlessly destroyed. For example, the pipelines are frequently diverted around trees, hedgerows are replanted, stone walls will be carefully dismantled and reconstructed. Naturally, underground services are also located and protected. Likewise, all topsoil, when stripped, is carefully stacked at the side of the easement and totally replaced on completion. The pipes are now delivered and placed parallel to the trench line. Burying the pipes comes late on in the spread process. Before, they have to be bent to shape, prepared and welded. Bending occurs to comply with naturally occurring contours or where the pipeline route changes direction. The bending engineer establishes the angle of vertical, horizontal and combination bends required with regard to the terrain and construction techniques being employed. This task is critical, and can only be undertaken after the topsoil has been stripped and pipes strung. Yet it also has to be completed to a demanding schedule so as not to halt the continual assemble line process. Details of the required angle and precise position for each bend along the route are then relayed to the bending crew, who cold bend the pipes using the purpose-built hydraulic pipe bending machine. Each push of the bending machine produces approximately a half-degree bend. This can be repeated along the pipe length to a maximum bend of 12 degrees. A total of 820 bends were formed over the 57 kilometers length. Some like it hot, and these are the pipeline pace setters. There will be up to 50 welders working along the line at any one time, mainly in pairs, and all using a stovepipe or down hand technique, which is relatively quick but requires considerable expertise. Indeed, each welder at the outset is tested to ensure that their work achieves the British gas standard PSP2, which is the equivalent of the American Pipeline Institute standard API 1104. As each pipe joint is made, the line is placed onto wooden skids at the side of the proposed trench. The 7 welders in the front welding crew make the first 3 passes or runs, these being an initial root run or bead performed by a trio of welders, a hot pass to provide reinforcement involving a pair of welders, finally the hot fill, again carried out by a pair of welders. Prior to the pipe ends being jointed, the ends are cleaned and preheated to the specified temperature. The following crew, known as the back-end crew, is comprised of pairs of welders with welding sets to make the filler and cap passes which complete the weld. Up to 18 pairs of welders are required on the back end to maintain the same output as the front-end crew. Note how the internal line-up clamp supports and holds together the pipes while the initial runs are welded. This is subsequently released and pulled through to the next joint to be welded. The welders always work in pairs to avoid any substantial variation in weld temperatures. The use of the 2 side booms to set up the pipes is a latter-day innovation that minimizes the delay whilst the next pipe is set up on the internal clamp. The side booms are specialist cranes developed for the cross-country pipeline industry. These are A-frames mounted on the side of Caterpillar tractors with movable weights on the opposite side to counterbalance the loads. Throughout the Cambridge project, an average daily weld rate of 92 was achieved with a maximum of 142. The welders spearhead the mechanical operations with their output governing the pace of all of the following disciplines. Quality is at the forefront of all pipeline operations, and never more so than the weld quality. Each completed weld is X-rayed and any defect either repaired or cut out and rewelded. Murphy Pipelines are justifiably proud of a defect rate of less than 1%. Passing on to another operation where an auger bore has just commenced, we can see within an hour or less the pipeline crossing yet another road. This method, as opposed to the traditional open cut technique, is the company's preferred mode for crossing roads and other similar obstacles, thus minimizing disruption and environmental damage. The work is executed by in-house specialists using company-owned plant and equipment. As you can see, a drive pit has been dug which can accommodate the crossing pipework and the boring machine. The auger or boring head has already been installed within the pipe and in turn connected to the machine. The whole assembly is lowered into the pit by side booms, which also hold the pipe throughout the process so as to maintain the desired angle of bore. The spoil from the cutting head is passed back through the pipe and deposited on the floor of the bore pit. Meanwhile, a reception pit has been dug on the other side of the crossing, and the operation continues until the pipe emerges. Whilst this highly effective method is used wherever possible, other alternatives such as open-cut trenches or pipe jacking are considered according to ground conditions, location, statutory requirements and resource availability. Back to the pipeline front end, and field joint coating is making steady progress about a half a mile behind the welding and X-ray teams. You will have noticed that the pipe ends are uncoated to facilitate welding. Once welded and the X-ray accepted, the welded joints are epoxy coated to form a continuous protective coating to the pipe as part of the pipeline corrosion system. To do this, the pipe ends are first grit blasted to Swedish standard SA 2.5 and then heated to approximately 250 degrees centigrade. The distinctive blue powder is then flock sprayed using a double rotating head spray system. This causes the powder to fuse and bond to the pipe. All the coated joints are further inspected for holidays, thickness and adhesion. The trench is excavated by three-wheel trenchers, working in sequence, which together excavate a trench approximately 2.5 meters deep and 1.5 meters wide. This will ensure the specified minimum cover of 1.2 meters over the pipe. These Murphy-owned specialist trenchers can excavate 1,800 meters a day, removing only the minimum of material necessary to achieve the required profile. Furthermore, the spoil is broken down such as to be more easily compacted following backfill. This process also leaves the soil suitable for screening to provide fines where otherwise imported material would be required for padding purposes. Now that the welded strings of pipe above ground have been X-rayed, the welds coated and the whole pipe coating examined for defects and repaired, they are ready for placing in the pre-dug trench. The pipe's flexibility allows a train of 5 side boom pipe layers to pick up the pipe string with canvas links and gradually snake it into the trench in a coordinated movement. Each side boom in sequence moves up to the one in front and takes the load, thereby releasing the one in front to move forward and relieve the next boom in line, and so on until the string is in the ground. The long sections of pipe welded above ground between roads, ditches and other obstructions, and now lowered into the trench, are then tied in together to produce a continuous in-ground pipeline. This normally involves cutting an overlapping section and making a single weld, or alternatively by the installation of a make-up piece requiring 2 welds. Following X-ray and coating of the welded joint, the remaining section of the trench is backfilled. The Murphy construction philosophy is to tie in the pipeline sequentially as soon as it is lowered in to allow subsequent operations to be completed without breaks, thereby permitting reinstatement to be completed at the earliest opportunity. Record progress was achieved on the Cambridge project by combining and supervising as one conglomerate operation the normally separate elements of crossings, lower and lay and tie-ins within a concentrated area. In this way, optimum utilization of the 9 side booms, 4 excavators, the auger bore equipment and 6 tie-in welders was achieved. The ultimate success of the Cambridge project will be judged by the degree of environmental impact both during construction and after completion. As has been underlined, both Murphy's and British Gas place great emphasis on ensuring that the pipeline will go unnoticed in years to come. In addition, the safe installation and its protection is crucial to its performance, and to this end, where the ground is unsuitable, the pipeline is encased in sand before the excavated soil is returned to the trench. Here, once again, Murphy Pipeline's readiness to use new technology and develop innovative new techniques meant unsuitable excavated material being screened by a specialized power screen, which was adapted and coupled to a D8 towcat. The resulting fines were such that they could be used to surround the pipe. This one innovation cut the need for an additional 300 lorry movements a day, as large quantities of sand would have been required, greatly reducing the environmental impact of construction. The backfilling is completed in layers and consolidated with vibratory compaction rollers or back-actor attachments. All subsequent operations return the surrounding environment to its natural state. Any ditches or banks that were disturbed are now reformed with care taken to break up any panning in the subsoil by ripping to allow efficient drainage. The remaining topsoil is then pulled away from the fence so the bulldozers can respread the soil evenly, fill any holes and generally level the surface prior to a final leveling by grader. The temporary fencing gives way to permanent fences which will border fields, resurface tracks and bridleways. Murphy's will frequently hand back the land in a better condition than its pre-entry status. To ensure the contract has been completed in accordance with the high standards set by British Gas, there are 3 principal tests to establish that the line is fit for commissioning. The Pearson survey ensures that the pipe is still free of defects after installation, backfill and reinstatement by passing a current through the pipe and monitoring the discharge on specialized surface equipment. The main mechanical integrity test is a hydrostatic test up to a pressure of 118 bar, although the operating pressure is normally around 70 bar. This is undertaken by in-house personnel using specialist plant and equipment developed and built by the company. A considerable volume of water is required for the test, and it is usually abstracted by agreement or license from rivers, streams, lakes or water mains, depending on availability and quantity required. In the event of insufficient supplies, the water can be passed from test section to test section. Due to the drought of 1990 and the consequent restrictions on water supplies, the planned main supply was not available when required. A joint British Gas Murphy effort located a lake about 2 miles off the route. With little disruption to the programme, the water supply and access to the lake were secured and testing resumed. The pipeline is first swabbed clean before each test section is filled with water and checked for air inclusion. Each section is then pressurized up to the required level and held for 24 hours. The resulting pressure and air temperature are constantly monitored on a Budenberg recorder. With the completion of the test, the water was discharged back to the lake and the test point was tied in to complete the pipeline. Finally, a geometric survey is carried out of the entire pipeline to measure any reductions in the bore. The survey is performed by specially designed pigs that are projected through the pipeline by compressed air at a controlled rate. Distance travelled, bore consistency, and the position of each weld are recorded. If there is a reduction normally greater than 5%, then the pipe can be exposed in the precise location by interpreting the chart in conjunction with the pipeline route drawing. The actual survey proved the bore was within specification, and the pipeline was accepted by British Gas and incorporated into the main gas transmission system. Now you see it, now you don't. Care for the environment, technological innovation, efficient teamwork, cost-effective quality, all cornerstones of the Murphy pipeline success story that make them one of the acknowledged market leaders. Whether it's routine maintenance or laying a multi-pipeline over some of the toughest terrain, you can count on Murphy's to get the job done without fuss, on time and with consistent quality assured.